High blood pressure, also known as hypertension, is a major health issue affecting many people worldwide. Currently, there are over 1 billion individuals suffering from this condition, and this number is expected to increase to about 1.5 billion by the year 2025. Those affected by this condition are at risk of heart failure, heart attack, and stroke. About 2/3 of those affected by high blood pressure live in developing countries, where access to healthcare may be severely limited. This means that traditional methods of monitoring blood pressure, such as the auscultatory method, are impractical for these communities due to a lack of access to electricity or medically trained personnel. Treatment of people with hypertension is frequently falling on state governments. In the U.S., treating patients with high blood pressure consumes 10% of the national healthcare budget. In developing nations, such as South Africa, it consumes 25% of their healthcare budget, or about 2% of their GDP. What this means is higher taxes and increased aid to developing nations to treat these patients. To solve this, we need a way to screen and diagnose large populations for high blood pressure. Treating the cause of the condition is much easier than treating the consequences. Blood pressure can be regulated through exercise.
That's it, hip track over here. Give me some energy. Side and round the world and lift, lift, and lift. Round the world. You got it, nice and tall.
Healthy diet, quitting smoking, and if necessary, medication. The first step for patient care is being aware of the condition. What makes this a problem in developing states is access to healthcare. In developing nations such as Zimbabwe, the patient-to-doctor ratio is 22,000 to 1. Even with ample volunteers, patients are still underserved. To properly diagnose a person with this condition, it requires 3 measurements within a 3-month span. This makes diagnosing patients for high blood pressure virtually impossible without self-monitoring within communities. In order to make self-monitoring possible, educating the users of our device is paramount. The idea is to have a rough screening of the residents in different communities over a 2-month interval, reporting this information to a doctor or medical volunteer. This allows valuable human resources to be applied with better precision. Another continual misfortune in developing world hospitals is that these hospitals have the necessary equipment to treat patients, but lack the ability to repair and operate this equipment. What is needed is a device that can assist in the measurement of blood pressure that is low cost, requires minimal training, and can be easily manufactured and distributed to developing regions. This is why we have developed the non-electronic blood pressure assist device. This device can be operated in conjunction with a regular sphygmomanometer in order to easily take a blood pressure reading from the arm. Similar to the auscultatory method, our device will detect the cord cough sounds associated with the flow of blood through the arteries. However, our device is designed to translate the minute auditory signal into a clear visible output, thus eliminating the need for training with a stethoscope. The device requires no power source to operate and is easily assembled onto the patient's arm to produce a clear indication of when systolic and diastolic blood pressure measurements should be taken. Our prototype consists of a metal enclosure similar to the bell of a stethoscope. It contains a circular opening on one end with a diameter of 45 mm and a smaller opening on the other end with a diameter of 5 mm. Attached to this opening is a series of rubber tubes and plastic connectors decreasing the diameter to about 1 mm, which then attaches to a capillary tube that remains open-ended. All junctions are sealed with epoxy, and the device is then filled with water dyed with a deep red color. The device is fixed to a detachable cuff secured by Velcro straps. Our device is designed to be used with a typical sphygmomanometer. The sphygmomanometer is secured onto the upper arm, while our device is secured slightly below it. Prior to inflating the sphygmomanometer cuff, the pulse of the patient should be seen, indicated by the periodic deflection in the water column. The cuff is then increased to a pressure of 180 millimeters of mercury. At this point, the pulsing in the water column should cease. As the pressure in the cuff is slowly dropped, the pulsing should eventually resume, indicating the proper time to measure systolic and diastolic pressure. In order to test the validity of our device, we simply compare the readings taken using our device with the readings taken using the auscultatory method. We decided to use this method of testing as our control
because the auscultatory method is the most common means of checking for high blood pressure. Based on this comparison, we determined that our device provided a reading that was adequate enough to determine if a patient has high blood pressure.
Our initial ideas for the device were derived from a blood pressure measurement method developed in the 1930s by German physicist Heinrich von Recklinghausen. This device, known as the oscillotonometer, allowed for the reading of both diastolic and systolic pressure without the use of a stethoscope. It consisted of two cuffs with a pressure gauge connected to one another. While the first, larger cuff detects pressure like a normal sphygmomanometer, the second cuff amplifies the patient's pulse as the first cuff is inflated. As the pressure in the gauge drops, small jumps are seen in the needle. When the jumps become stronger, a dial on the cuff is triggered, causing the gauge to become fixed on a reading of systolic pressure. As the cuff continues to bleed, the instance of maximum deflection serves as a point of mean blood pressure, which is once again read by triggering the dial. Finally, when the amplitude of the jump suddenly begins to diminish, diastolic pressure can be measured.
We considered a variety of different designs before deciding on our prototype. For our first prototype, we constructed a double cuff sphygmomanometer connected together to a single hand pump. The lower cuff acts as a pulse detector, while the upper cuff provides a pressure reading. The issue with this prototype is that it took a significant amount of time to pump, only achieved a very weak detection signal, and was much too large and bulky, making it confusing to use. We also considered other crafty detection methods, such as the use of a null pressure gauge, refractive glitter, non-miscible fluids, an audible whistle, a floating ball bearing, and a mechanical bandpass filter. These innovations, though, would add an extra layer of complexity to the design of our device, which would call for more specifically designed components. This would ultimately increase the manufacturing cost of our device.
For the null pressure gauge, the concept is to remove outside motion from disturbing our signal by splitting the water column and having the opposite sides push against each other. This results in a net displacement only in the vertical direction. This was ruled out due to difficulty in prototyping and manufacturing. With the mechanical low-pass filter, the concept is to remove higher frequency oscillations from interrupting the signal. We would start by constraining the diameter of the tubing to increase the resistance, and then having the tubing bifurcate, one portion going to the detector and another going to a compliant membrane. This membrane acts as a capacitor, as it will absorb energy of higher frequency oscillations caused from shaking. This was ruled out because of the material concerns, extreme difficulty in prototyping, and signal strength reduction.
There are a number of reasons why we decided on our prototype design. Considering the problem that we are trying to address, we expected our device to be simple and straightforward by nature. Our prototype device has shown to most closely follow our design criteria. The design of the device, as well as the operation, is both clever and intuitive, offering an effective solution to monitoring blood pressure without the use of electricity or expensive components. Due to its simple visual output, our device can easily be used in regions worldwide with minimal training. In order to use our device in our target areas, it is necessary to get approval from the regulation groups of their respective countries. If we were to administer our device to Tanzania, for example, it would be necessary to get approval from the Tanzania FDA. Based on their standards, our device is of a Class B risk, which is defined as any active device intended for diagnosis, if they are intended to allow direct diagnosis or monitoring of vital physiological processes. Overall, the development of our prototype costs no more than $20. This price may be lowered even more if the device was produced on a larger scale. The affordability of our device makes it a great candidate for a product in a global market, especially in countries with a limited healthcare budget. Through the course of this project, we have learned that sometimes a simpler approach proves to be the most effective.
I fear I can't take it There's nothing else to show for all of the days that we spent.
When do you want to introduce it?